Welcome everyone to our discussion on an innovative framing of integer division, focusing on a technique that rethinks remainders as active, signed correction terms. This approach is called REIST Division, Remainder Extended Inversion and Subtraction Technique, and it essentially shifts the classical mindset of non-negative remainders to a centered symmetric interval.
Right. The idea is to allow remainders to be both positive and negative. So instead of the standard interval 0, b, REIST uses a centered interval, like b over 2, right?
Exactly. And this subtle change actually has several practical advantages. Rather than the remainder being a passive leftover, it becomes a correction term, essentially an adjustment that tells you whether the nominal quotient is overestimating or underestimating the true value.
Interesting. And I guess that makes a big difference in applications like cyclic systems and digital processors, doesn't it?
It sure does. The technique is particularly well suited for cyclic or periodic contexts, think scheduling tasks, digital signal processing, robotics, or even CPU microarchitecture where feedback loops and error correction come into play. In these systems, having a remainder that can be negative provides a balanced, symmetric representation, which naturally minimizes drift.
Yeah, that makes sense. So, can you help me understand how REIST reframes the classical division formula?
Of course. In classical division, we have t equals q times b plus r, with r forced to be in 0 to b. But in REIST division, we still decompose t as t equals q times b plus r, except that r is constrained to fall within this centered interval, b/2, b/2. This means that if t would normally produce a remainder near b, it can instead, be interpreted as a smaller negative value. For example, take t equals 17 with b equals 10. Classically, 17 equals 1 times 10 plus 7. But REIST gives 17 equals 2 times 10
Right, reducing
minus
the absolute
3.
deviation. So in that example, rather than a remainder of 7, which is relatively large, REIST delivers a remainder of -3, effectively bringing the error term down in magnitude, correct?
Exactly. And that's the core benefit. It minimizes Barks-Yergeau. The quotient is chosen such that the absolute remainder is as small as possible. This is particularly useful in iterative processes. If you have repeated operations, classical division's asymmetry can lead to drift over time, but REIST actively resets that drift by using the best correction, whether positive or negative.
I get that. Now, I remember something about even moduli being a bit tricky here. With even b, there are two possible representations, right?
Yes, that's a good point. For even b, the centered interval is ambiguous at the midpoint because you can have both plus b over 2 and minus b over 2 representing the same congruence class. REIST resolves this neatly by always selecting minus b/2 as the representative candidate, so the positive half boundary never occurs.
That's a smart tiebreaker. It certainly keeps everything deterministic and consistent. So, apart from the theoretical appeal, do we have any empirical evidence showing that this method improves performance in real systems?
Yes, indeed. The evaluation spans modern CPU architectures, ARMv8A and x86-64, for instance. The benchmarks reveal impressive speedups, especially for modular addition and polynomial modular addition, which are critical kernels in lattice-based cryptography. On ARM, for example, there are speedups of about 2.5 times for synthetic modular add counters and up to 6 times for polynomial modular additions.
Yep, that's significant. And how about the x86-64 results?
On x86-64 architectures, the speedup is even more pronounced, with roughly 9 times improvements for modular addition, and in the case of polynomial modular addition, enhancements up to 15 times under full optimization. The key insight is that REIST avoids the costly division instructions by replacing them with branchless operations, primarily additions, comparisons, and subtractions.
Very impressive. So it's like the REIST method is plugging into the CPU's arithmetic unit in a way that better aligns with its native strengths, particularly in SIMD operations, right?
Absolutely. In fact, one of the most exciting aspects is its inherent SIMD compatibility. Because the correction rule is branchless and independent across lanes, REIST maps naturally to vectorized operations. On ARM's Neon SIMD, for instance, the performance
that's a
can
game
almost
changer
double
in terms of
compared
parallel
to
processing.
the scalar implementation.
But can we really say that REIST is a replacement for classical modular arithmetic? Or is it more of a targeted micro-optimization for specific workloads?
It's definitely more targeted. REIST isn't a universal solution that replaces every use of the classical remainder. It shines in scenarios where modular addition is a bottleneck, like in cryptographic algorithms and cyclic systems. However, for operations that don't involve modulo reductions, like ARX-based ciphers such as CHA-20 or hash mixing functions that depend on multiplicative diffusion steps, REIST doesn't provide any advantage and may even be slightly
Yeah, that sounds like a
slower.
prudent specialization. I see. And how has the community reacted to this reframing?
The feedback has been quite rich. Initially, some thought that the proposal was trying to redefine integer division globally. But the emphasis has shifted, thanks to community review, to understanding that REIST is simply a reinterpretation of existing theory with practical implementation advantages. Even critical experts acknowledge that the branchless structure, which eliminates heavy division instructions, can, in many cases, reduce register pressure and lead to more efficient
Got
code.
it. While that's compelling, do you have any reservations or critiques about this approach?
Sure, one could argue that REIST's improvements are somewhat limited to specific benchmarks, and that, in scenarios where you aren't heavily reliant on modular additions, the benefits are marginal. Also, in the context of, say, full remainder computations, where we're not just adding modulo, but actually computing the modulo operation, REIST performs very similarly to the classical method, with only about a 5 to 12% difference in runtime. So it's not an across-the-board replacement, but rather a specialized tool.
Yeah, that's a fair point. And this makes me wonder, do you think the algorithmic community or hardware designers will explore further integrations of this approach, maybe even beyond arithmetic and cryptography?
Oh, definitely. There's been discussion about potential applications in supply chain logistics, cyclic scheduling, iterative numerical methods, and even predictive modeling. Essentially, any system that benefits from minimal corrective adjustments and symmetrical error feedback could theoretically leverage REIST division. It's like optimistic feedback control in arithmetic.
A mathematical tool that's as much about error correction as it is about basic computation. Do you think it might eventually influence compiler designs, perhaps by providing an alternative lowering strategy for modulo operations?
That's an interesting thought. Since the REIST formulation maps so neatly onto branchless, SEMD-friendly sequences, there is potential for compilers to recognize when the typical modulo pattern can be transformed into a REIST-style operation. This could lead to optimizations for high-performance modular arithmetic kernels, particularly in cryptographic libraries where every cycle counts.
That sounds like a fruitful area for future research. I also noticed the report mentioned further research directions. What are some of those?
There are several promising directions. For example, formalizing REIST within algebraic ring structures, exploring constant time implementations to address side channel risks, and even hybrid operators that blend REIST with classical modulo methods for multiplication-heavy workloads. Moreover, implementing REIST on newer architectures like RISC-V or even on GPU
that's quite broad and
platforms
forward-thinking.
is on the horizon.
It's impressive how a small shift in perspective can open up so many avenues. But do you think there's any risk in shifting the traditional, well-established definition of remainders, even if only for implementation purposes?
That's a valid concern. But it's important to clarify that REIST isn't redefining the arithmetic in a way that changes the underlying algebraic structure. It's more like changing the coordinates in which you express the same number. They're mathematically equivalent. The classical identities still hold. We're essentially just choosing a representation that's more aligned with how modern processes work.
I see what you mean. More like adopting a different lens, not a new arithmetic system. And this shift to a symmetric remainder seems to be particularly effective in reducing what they call cyclic drift in iterative processes, right?
Precisely. In cyclic systems, classical division tends to accumulate error in one direction because it only allows positive remainders. With REIST, the remainder can actually indicate if the system is leading, positive, or lagging, negative. This feedback can be crucial in, for example, phase alignment in digital signal processing or in scheduling corrective actions in robotics. It's all about keeping the error minimal and symmetric.
Yeah, that's a very elegant solution. Are there any areas where REIST falls short?
Well, as we mentioned earlier, for workloads that are not dominated by modular addition, like hash mixing or certain ARX cipher operations, the advantages disappear or can even be marginally negative. That's because REIST is specifically tailored to eliminate the bottleneck of costly modulo operations and isn't a one-size-fits-all performance booster. So its adoption should be strategic,
Selective application makes sense in engineering.
Context where its benefits are clear.
Given this, do you think REIST will change how cryptographic libraries or systems are engineered?
It's definitely possible. Especially in lattice-based cryptography, where the dominant workload involves polynomial modular addition operations, the speedups, especially on x86 to 64 architectures where they've seen up to 15 times improvement, could be a compelling reason to adopt REST-based routines. That said, it's more of an alternative tool than a universal fix, so its implementation would likely be limited to hotspots
tailoring
where
optimizations to the
performance is
workload
critical.
is always the smart approach. Summing up, REIST Division seems like a thoughtful and practical reimagining of an old arithmetic concept, with real-world benefits in certain high-performance contexts. Am I getting that right?
You've nailed it. We're not reinventing arithmetic, we're reinterpreting it, focusing on that signed correction for remainders to better interface with modern computational demands. It's a targeted, efficient, and mathematically equivalent approach that has practical implications, especially in cryptographic and cyclic systems.
Yep, absolutely fascinating. Thanks for this deep dive into REIST Division. It's been an engaging conversation, blending theory with hands-on benchmarks, and really highlighting the engineering intuition behind it.
Thank you for the great questions. And thanks to everyone listening. Keep exploring those innovative angles in computation. And until next time, happy number crunching.